Okay. Thank you. And today we have Professor Somnath Baidya with us from IIT-Delhi. And Professor Somnath Baidya is not new to IITM. He has been visiting IITM, and then he has a collaboration with different. So he's a well-known person in the field of land atmosphere interaction and renewable energy meteorology. Now he is going to show. So, but I wanted to give his bio in brief. He has done his BSc honors in physics from Presidency College in Calcutta and MSc Environmental Sciences from JNU New Delhi. And he did his PhD from Reuters University, New Jersey, USA. And currently his activities are he is editor-in-chief of Earth System Dynamics and then a co-convener of Wind Power Meteorology European Geosciences Union General Assembly. And I think many big platforms has commented on his works, and then they have just reported like Guardian, BBC, and then German Public Radio, NASA press release, and Nature editorial, New York Times. So he's like an international recognized scientist, and he's a professor at Center for Atmospheric Sciences at IIT Delhi, and he went to US for graduate to school, but stayed more than 18 years. I think it's a long time. Working as a postdoc in Department of Ecology and Evolution Biology, Princeton University Environmental Institute, and then the Department of Civil Engineering at Duke University, and then Department of Atmospheric Sciences, University of Illinois at Urbana-Champaign. And then after that, in 2013, he joined at IIT. So currently, he is the head of department of Center for Atmospheric Sciences at IIT Delhi. And we are looking forward a very interesting talk. Basically, you can see that representing wind farms in weather and climate, which is actually renewable energy meteorology, and this is a future. So I request Professor Vaidya to deliver his talk.
Hello. Can you hear me? Okay. Thank you, Dr. Tiwari, for that very great introduction. So, like, I'm coming back to IITM after a long time. I mean, I have been here earlier multiple times, but because of Corona and then lots of job responsibilities, there was a long gap. And so when Dr. Krishnan invited me for this brainstorming meeting tomorrow, I thought I will come by and meet with him and many of my older collaborators and ongoing collaborators as well. So today I'm going to give a talk on a topic that perhaps will be new to you. This is very few people in India actually are working on these areas, but it is an upcoming area even in the Indian context, the area of renewable energy meteorology. 2008, European Geosciences Union has its first wind energy meteorology session. And I've been associated with that since 2010 for the last 13 years. And now we call it energy meteorology. So it has gone from wind power meteorology to energy meteorology. The thing is happening here in India, but before I'll come to that in a moment, but let me tell you what area is all about. So basically here we look at the meteorological aspects of three things: resource assessment, forecasting, and impact assessment. And these all have very important roles in. Thank you. I teach, so I can speak loudly and often for a long periods of time. If I start, I talk for 55 minutes. Yeah, I'll try to finish in 45. So resource assessment is something that you need to understand. Where am I going to put my wind farm? Forecasting is very important because if you recall that wind and solar are intermittent, right? But our electricity is not intermittent. We want it all the time. So when suddenly if wind goes up or falls below a level, these can destabilize the grid or create power cuts, and that is not something that we want. So that is why we need forecasting so that we can manage these ups and downs. And obviously impact assessment, any kind of large scale projects, we need to know how that is going to affect, and then do a cost benefit analysis in terms of the atmosphere and the environment. So wind energy, as we know, it's growing steadily. Right now in India, we are fifth in the world in terms of wind energy. So we are very close to 1 terawatt that way in terms of wind from 2021 to 2022, these 20 years. Along with the growth of wind energy, another interesting thing that has happened is the increase in size of turbines. So when we started, if you look at in the early 80s, small turbines, 20 meters tall, 20 meter is just 6 stories. It's relatively small compared to today, the turbines that we have are more than 150 meters tall. The rotor diameter is also 100 meters. So if you put this together, we are talking about structures that are 250 meters tall, and a lot of them placed very close to each other. 250 meters is more than 80 stories, one of the tallest, close to as tall as some of the tallest buildings in the world. Here for reference, you can see I think an aircraft, and that's how big a wind turbine is. Now, along with anyways, can I next? But hopefully. So, along with growth in wind energy, growth in wind turbines, what has also happened is growth in wind farms. I'm just giving you two examples. Okay, so this is West Central Texas. This is about 10 kilometers. You can see these are different wind farms and how densely they are packed. There are about one wind farm every kilometer, one wind turbine per kilometer. And this is how densely they are packed. If you look at North Sea, these are the distribution of the wind farms. So very, very densely packed. So we are talking about very large structures packed very densely. Now, what does it mean for the atmosphere? I'm going to start with something very basic, the Lorentz energy cycle. You all are familiar with. So what Lorentz said, that you have the zonal mean available potential energy and the turbulence potential energy. They are converted into either zonal mean kinetic energy or turbulence kinetic energy, and then finally dissipated due to friction. Very simple. So let us look at a Lorentz curve that people have, Kim et al. Have looked at relay analysis data and tried to find the numbers. So here, these are the reservoirs of energy in kilojoules, and these arrows give the fluxes. So if you look at fluxes, the order of magnitude of the fluxes is 1 to 0.1, right? This is dissipation of kinetic energy. That is 1.16 watts per meter square. So if I take the whole world, look at the rate of kinetic energy dissipation, that is about 1 watt per meter square on an average. Now, let us look at a wind turbine. Okay, so if you consider a wind turbine that is spaced, say 100 meters rotor and 10 rotor diameter, which is typical, it's a small turbine by today's standard. So that is, which means 1 turbine per square kilometer. So there, the turbine is extracting energy at the rate of 1 watt per meter square. So a turbine from 10, 15 years back has an impact which is equivalent to a natural process. So immediately you know that this is something must be affecting, especially when you have densely packed turbines over large areas. There has to be some impacts. So this is something was that drove my interest in this particular problem. And so what I did, as a modeler, mesoscale modeler, I wanted to see how does it interact with the environment, what happens. So we started by building a parameterization for wind turbines. And so I started with this particular concept. So if you look at a wind turbine, there is energy coming in, right? And the wind turbine takes some of that energy, converts it into electricity. So there is less energy now, the wake. So the wind turbine is a sink of momentum. Another thing, in the wake of a turbine, there is a lot of turbulence. It's coming because of the rotation of the turbine, and also because there is a momentum deficit. So by simple K theory, because of the gradient, there will be turbulent eddies that are forming in the wake. So now, actually, if I just go back to the title of slide of my talk, you can see these turbulent eddies. This is a picture from the North Sea taken in February 2012, I believe. So these are turbines, and you can see the wakes because it was very stable and humid on that day. So it actually formed low-level clouds. Okay, so we can see this turbulence. Now, so with this in mind, this was my parameterization. It is a source, a sink of
clouds because of the
yes,
because of the turbine.
yes, you can clearly make that connection. And so now a lot of people, pilots, that's their amateur pilots, their hobby is to go and take the pictures of these clouds in the wakes of the turbines. So people think that this is like a cartoon, but this is actually a photo. So you can Google it and you will know who took it, all this information is there. So that's what, using that, I built this parameterization. So if you look at the horizontal momentum equation and the TK equation, so what we did is we added a sink term to the momentum and the source term to the TKE. And so now the challenge is what are these sources and sink? So for this particular paper, I mean, it was a very simple paper. This was the first time. So what we did is this is the power consumption, power generation by a turbine. Half rho Cp A V cubed. A is the area, rho is density, Cp is something called the coefficient of performance of the turbine. Power coefficient. So I just assumed a constant 4. That means the turbine has a 40% efficiency. This is not strictly true. Turbine efficiency is a function of wind speed, and the maximum limit is 60%, 59%, Betz limit. So 4 is but still it's a reasonable number. How much of the kinetic energy can be converted to power? So that is, there is a theoretical limit called the Betz limit, that is 0.59, 59%. So we took 0.4. A is the area, rotor diameter. So basically, it's pretty straightforward. You calculate how much air is passing through. That is rho times A times, that is A times V square. And momentum is mass times velocity. So mass is rho times V times A times V square. So rho A V cube. Cp is just the performance efficiency. 59 is the maximum from theory. So we took 0.4, 40%. And R is the amount of TKE. So we had some observation that tells us that what is the TK in the wake. So using this, we built this parameterization. And then this was a simulation. First time in 2004, we put a wind farm in Oklahoma, in the middle of the Great Plains. And if you look at the results, you can see that there are two scenarios. This has only the momentum sink, and this is both momentum sink and TK source. You can see that the wind farm is actually taking out energy from the atmosphere, and this is matching the power production. So it's working okay. And also we looked at the vertical profiles of the wind speed and temperature and humidity. One interesting thing that we see in the temperature, for example, this is the hub height. So the temperatures are slightly cooler, warmer at the ground. Okay, so this was the finding of this paper.
Scenario 1.
So scenario 1 is just the momentum sink, and scenario 2 is both momentum sink and TK. So 2 of these cases. So this particular warming at the surface, that was very concerning to a lot of people. So, and people kept on saying that this is just a model. No, I mean, you are telling wind farms are actually creating a warming. How is this possible? So,
The scenario it reduces.
it's lower because the turbulence that you are generating, that is actually coming from the mean wind. For kinetic energy, mechanical energy balance, so first you take out energy from the mean wind to generate power. Then you take out some of that energy and convert that into TKE. So that is why, like, you have less energy available for the downwind turbine, and that's why this is lower.
At what height?
This is a 100-meter tall tower. This is a 100-meter height. Then what we did is, like, I worked very hard, like trying to find some data, something. And then Neil Kelly at the National Renewable Energy Lab came to my assistance. So there is this San Gorgonio Pass in California. There is a big wind farm there. And so this is a satellite image of the wind farm. You can see the turbines, and these are the roads that connect these turbines. And this was the structure of the wind farm. And so he had like an upwind tower and a downwind tower. So by measuring the difference between the two, we can get a sense of how the wind farm affects meteorology. So this is what we found. The tower was 5 meters tall. So what we found was that during the daytime, we see a slight, like downwind tower is warmer. And sorry, during the night, we see a slight warming, and during the day, we see a cooling. And so I looked at the stability also, that during the day, 4 a.m., it's stable, and the other two are fairly unstable. Okay. So with this kind of observation, we put together this hypothesis. So let us take a wind turbine. You have the incoming wind. It is generating some turbulence in the wake. Because of this turbulence, now remember, during the daytime, it's warm underneath, cold aloft. That's the eddy, okay? And during the nighttime, it's warm aloft, cold underneath. Now, what happens is that when you have, like, because of this turbulence, you have mixing, right? So what is happening is that at night, it is bringing, at day, it is bringing the cold air down, pushing the warm air up. At night, it is taking the warm air down and pushing the cold air up. So basically, if this was your diurnal energy cycle, now under a wind turbine condition, this is to look like much more damped temperature cycle. So this is the hypothesis. And if you look at our data that supports this hypothesis, we also did a number of simulations where we connected the delta T, the warming, with the lapse rate. And as you can see, positive, as it's pretty much straight line, that as the lapse rate is potential temperature lapse rate, as it's positive, causing a warming, negative, causing a cooling. Now, again, like, these are limited observations. But since then, lots of people have started looking at these wind farms. And there are many, many papers that look at impacts of wind farms, not only on meteorology, but also this has now, I'm not going to cover all of them, but also surface fluxes, surface temperature, air temperature, even GPP and NPP. That how this mixing affects, because a lot of the wind farms in the US are in agricultural land. So for example, I'm showing like, two images from MODIS, where you can see that the nocturnal temperatures over the wind farms are warmer. These black dots are wind farms. This is over Illinois. You can see that the nocturnal temperatures over the wind farms are warmer. And there is plenty of evidence that this is happening, that there is some warming. Now, obviously, you can see this work that we did. There was like it became a major news story. So New York Times had this article talking about that wind farms are actually affecting climate. And it led to a lot of negative repercussions for me, where people are very passionate about energy. So I had to deal with like, a lot of hate mail, phone calls and other things. And finally, actually, Nature in 2011 published a editorial where they strongly supported my work. For example, they said that some took his study as an attack on the wind industry, and he was besieged with nasty emails. They questioned his sanity. threatened to get him fired from his post. It was at Illinois. Anyways, all of these things. But important thing is nature said that some legitimate questions have been raised and politics must not block research where it should or where it's needed. Now, anyways, so that aside, like, I mean, even though it was a beginning work, a lot of people were skeptical. Now I see many of them, scientists actually involved in this particular activity. And what it has happened, done is, it has led to this explosion of papers. Like a large number of papers on first, how to parameterize wind farms. There are two approaches. One is implicit, which is wind farms are just a surface roughness element. The other is explicit, which is basically what I did, is wind farms are momentum sink and TKE source. And beyond that, there are tons of applications of this parameterization, from characterizing flow effects, environmental impact, wind energy planning, like resource assessment and wind theft. So I'm going to just briefly, like, yeah. Right, yeah. Yes. So basically, like, what happens is that if you look at the wind energy profile, it has a vertical structure. Okay. So for example, if you see, you have a cooling here, warming below. If this is your roughness element, you will not have the vertical structure. So in these parameterizations, the wind farm is something aloft. So things can happen above, things can happen below. It's a surface roughness element. It is just connected with the surface. You do not get any vertical profile in the surface layer.
You have a logarithmic profile, right? Or somewhere aloft. Logarithmic.
It can be done. It can be done. Like, I don't know that the profile is not necessarily logarithmic all the time. So, but if you are connecting it with the surface, then you don't get that vertical structure of the wind farm impacts. And there are other studies which have compared also show that.
Levels you have in.
So, different models do it differently. So in mesoscale models, it's very easy. If I recall in WRF, what I did in RAMS, what I did is, I think my mind 20 years. So I think the height was at 100 meters. So I took that level to be 100 meters and I put 2 layers underneath and then multiple layers aloft. But people choose their own resolution depending on the height of the turbine. So what is happening under the wind farm turbine and what is happening above the turbine, you lose that structure completely, and that tends to overestimate the impacts in roughness element. So, yeah.
Consider energy equation.
So in models, there is no the kinetic energy conservation equation is the Navier-Stokes equation. So it conserves thermal energy, but there is no direct impact of wind farms on thermal energy. So the only thing it affects is dynamics, and any effect on thermodynamics and microphysics is indirect from the turbulence. So these are the different parameterizations that are available since then. There are 10 of these, and I'm only talking about the explicit parameterization in mesoscale models. GCMs have, many GCMs have like a roughness length type parameterization. And the most popular one of them is pitch, because this is the default parameterization. It has actually now been modified by Pan and Archer. So that is available in the WRF model. So this is from this paper overview of wind farm parameterization in boundary layer meteorology. So what Fitch did basically take that same approach that I had, but they said that you have to have a better way of characterizing the wind farm. So they look at properties of a turbine. So this red line is called the thrust coefficient. This is the total amount of energy taken out by the turbine, including the structure. And that is a function of velocity. The green line is the power generated by the turbine, which is also a function of velocity. So what Fitch said that the thrust coefficient is power coefficient plus TKE coefficient plus mechanical losses. And ignoring mechanical losses, I can calculate the power coefficient. I had assumed a 40% efficiency. Here you can, this is the efficiency, they varied it with wind speed and said the difference between the red and the green line, this is and then here, that's the TKE. So I think that is a much more reasonable way because it is coming actually from data. And all the other parameterizations are kind of, I think, fundamentally modifications of pitch, like, what reference wind speed to use, how do you estimate the coefficients. Blahak et al. Accommodates mechanical loss. I think Portugal and then Redfern, they take into account subgrid processes, but these are, I feel, minor adjustments. Holkar et al. Is a completely different approach. So again, they took completely subgrid. They characterized the wake inside a grid cell. That gives them how much momentum is required to generate that wake. So these are the three different kind of, or two major and like perhaps three minor different approaches that we have. And these have been extensively used. So for example, like, you will see, as I said, WRF is the most common model because the Fitch parameterization is default. So you download WRF, there is a wind turbine parameterization. You can use it. And these are the studies that have been conducted across the globe for this kind of using wind farm parameterization. And these results have been extensively validated by many different type of instruments. Most of the common validation is TKE, wind speed and power, but many validations with like, precipitation, pressure, surface temperature, and so on and so forth. So I'm going to give you one example of a validation because there are many, many studies. So this is from Sidleberson et al. They did this work over the North Sea wind farm, and they had an aircraft flowing back and forth in the wake of the wind farm. Okay, so let us look at this data. Okay, so this is the WRF model simulation of potential temperature and mixing ratio. So these are the wind farms. Okay, so this is these blue lines are the wind farms, and you can see that as you go downwind on the wind farm, there is a warming and there is a drying downwind on the wind farm. And if you look at the airplane flights, you can see that same warm and the cooling and the drying or the moistening in, the drying behind the wind farm. So there are many such cases. Okay, there are many such these kinds of examples where people have taken this parameterization, tried to evaluate it. It's very difficult to capture the magnitude, and that's something that we need to work on. But the broad patterns everybody is able to capture. The second thing, like, what we learned from these wind farm parameterization simulations is this is how a wind turbine interacts with the atmosphere or a wind farm. So first you have the coming wind that kind of slows down. That's the blocking effect. Then it travels around the wake, around the farm. Some go over, some go around. So these are kind of loss in momentum. You have wake effect inside the wind farm that as they are drawing power, they are reducing the momentum availability. You have wake recovery because of vertical mixing, because there is a momentum deficit. So high momentum air from top will come and try to replenish that. And then finally, you have wake recovery by horizontal convergence. So we are able to now look at all of these separately. And I'm going to give you one example of that. Okay. So this is one of my students for a PhD is looking at a wind farm in just offshore wind farm, no effect of land in the middle of Arabian Sea, just a hypothetical wind farm. So if you can see, did three different cases. These are the incoming wind direction. You can see the power generation. But very importantly, you can also see the wake. This is the statistically significant like wake. So the wake in this particular case, when the wind was very strong, it lasts like, hundreds of kilometers. And it is indeed true. People have found signals of wakes from wind farms 50 to 100 kilometers downwind. So that's the length of the wake. This was in the model, but many of them are small, but this one is quite large. Then what we did is like, characterize the two types of recovery that we said through vertical turbulence or horizontal advective mixing. And as you can see that vertical recovery replenishes 60 to 70%. Horizontal recovery is very small, of the order of 10%. So typically, is 1 kilometer. And so we did these experiments. So like here, I think it is, yes, 1 kilometer. So here we put 4 turbines. Here we put 1 turbine, and then here we put 1 alternate turbine. So 500 meter, 1 kilometer, and 2 kilometer spacing. So you will see three different cases. Cases, and these are the three wind speed cases, A, B, and C. So vertical recovery and horizontal recovery, subgrid scale, basically we calculated the subgrid scale recovery, different types of fluxes, and then we added them. So vertical recovery dominates the horizontal recovery. Going to another interesting thing. This is an interesting so that this is a front. This is an old work, a front passing through a wind farm in Texas. What we saw that initially, because of the blocking effect, the frontal system slows down. But once it enters the wind farm, because the wind speeds are lower, so it tends to speed up. So you can see this front and the difference in the wind, that here it's faster and here it's slower. So these are lots of interesting things people can do. But now I come to the last example. So we've talked about environmental impacts. We've talked about flow characterization. The last one is about resource estimation. So if you look at a wind farm, this is the wind that is coming in. This turbine is taking out energy. There is less energy for the wind turbine. Now, if you go and work in for like any large renewable energy company and they ask you to give them a map of wind resources, and you can search for this, you have something called wind power density. Okay, so basically that is a map of wind speed. And if you look at, there are lots of papers, we say that there are 100 terawatts of energy available. Because what they are doing is they are taking the wind speed and then multiplying it by 3 to get terawatt hours. Now, think about this, like this wind farm, this is the raw wind speed for this turbine. For this turbine, it's much smaller. So unless you account for the fact that downwind turbines will have less energy to work with, what you are getting a serious overestimation of wind energy. This is something Volcker did. So what they did is two different parameterization. This is the Volcker's parameterization, and this is the parameterization. They did this model, the simulation, and saw that as your wind power farm becomes bigger and bigger, your estimates, error in your estimates become bigger. And this is a problem. So I can challenge you. You can go and talk to any large wind farm and they will say, when I did the resource estimation and I calculated how much energy I'm going to get and how I'm going to sell it and what is my return on investment, they are all lower than that estimate. That is primarily because that nobody takes into account the wake effect when estimating resources. So that's a very important thing. And there are a series of papers on this particular topic as well. So for example,
it also where you're putting direction of the wind.
Right. If it's not downwind, then this effect is not there, of course. But the thing is that, if you look at the strategy, everybody wants to capture the maximum wind. And I'm going to come to a very interesting problem just in the next slide about this. So obviously the wind is coming. If there is plenty of wind for everybody, no problem. You can draw a straight line of wind turbines. But because of land and other restrictions, you have to put them one after the other. So there are lots of restrictions. And this is what, this study by Max Planck and DTU, they did. This is how wind farms are typically, they are saying 550 watts per meter squared that cross a wind turbine. Okay. And they assumed a 2 watt per meter square recovery. But they also assumed a strong wake effect. So here you have the wake effect and you have the recovery. With these studies, what they found is that if you do not incorporate wake effects, then you can, as you increase the size of the wind farm, your power generation increases. But if you incorporate wake effect, as you increase the size of the wind farm, your power generation decreases. So they said that let us not put big wind farms, let us put small wind farms separated by a distance so that we give the atmosphere enough time to recover the lost momentum. One interesting application of that is this is from a modeling study, is that of wind theft. Okay, so we put a small wind farm in the Park Strait, tiny wind farm, I think 50 by 50 kilometers, something like that. This is the in the Park Strait. during the monsoon and the return monsoon, you see this is the wind direction. So we did some simulations. So we took the wind farm and we put one wind farm just ahead of it, small wind farm, same size. We put another wind farm that is double the size. This is another wind farm that is kind of like blocking all sorts of. And then we just added 2 rows of turbines. So we see that in each of these cases, we can lose power by almost 27%. So almost a third of the power loss can happen if you build a wind farm and somebody puts another wind farm in front of you. Think of this, like you have built like a very nice house in the beach of Goa. Okay, someone comes and builds a house right in front of that. So what happens? This is exactly what happens. And in many places, there are laws that prevents you from stealing the view with the view shed concept, right? So, but we don't have that kind of wind shed concept. So that is why wind theft is a very common problem. Sometime back, like 10 years back, there was a legal judgment of 20,000 euros because someone had built a wind farm. Another person came, and so when you build a wind farm, you lease land. Now, what they did is like, so they leased the land for the turbine only to save money. Another person came and put a wind turbine in the middle of their farm. So, and that way the farm was losing money of 20,000 euros per year. So now, after that judgment, when someone leases land, they take the entire neighboring land with some that you cannot sell it to in farm company. So these kinds of things have happened. Anyways, so these are like, some of the, just to quickly summarize, like I think what we have seen is that wind turbines, wind farm parameterizations are effective tools for studying wind farm dynamics. They are able to replicate observed patterns in meteorology, and the simulations have interesting findings. First, there are environmental impacts. These are non-trivial, but there are studies which have compared that what is the impact of climate change, what is the impact of a wind farm that can reduce that climate change. And they find that like, the impacts of wind farms are non-trivial. So there is still a net benefit, climate benefit of wind energy. And the wake effects are crucial for resource assessment. So regarding future work, I think there is a lot of things that we can do, like, validation and characterization. Most important thing is that how do we, like, interact, make the wind farms interact with other physics, thermodynamics, microphysics. So that's one thing that we are trying to look at. Finally, I don't know. Yes, this is something like, perhaps in the future where we can have a platform that can seamlessly forecast like wind speed and power by using a wind farm parameterization. So with this, I'm going to stop and see if there are any questions. Thank you.
Thank you, Professor Baidya. It was really a very interesting and insightful talk. And there are a lot of information, new informations. So we can discuss. Yes, sir.
Thank you very much, Professor Somnath. I really enjoyed your talk. See, sometime in early 2000, we had many monsoon failures. Right, 2002. Many areas, Marathwada and all. In 2004, or I don't remember, Pansab was the director. Somebody raised this issue that these wind farms are there on the Western Ghats, and I think he was also politically connected. So whether it is affecting the rainfall and watch, one committee was also set up for this. Find out whether it is affecting. So what is your? I will come to what was the committee's assessment. Now you can tell me.
So, I mean, I think I know what you are saying because I used to get mostly farmers group from Maharashtra contact me and like, with this, that the monsoon failure or rainfall failure is happening because of wind farms. There are lots of people from China also used to contact me and many of my co-authors and other people in this field that this thing is because of like, wind farms. So that's what I said, that like now our connection between wind farm and rainfall, the physics of it is not very well developed. That's something that has to be done. But most studies that have looked at, so first of all, my opinion that if you can see that the impacts of the wind farms go fairly high up, like, several kilometers, but obviously not as deep as any kind of cumulus convection. So it will be very difficult for a wind farm to stop rainfall. And though simulations have shown that when you have extremely large, like people have done, like entire southeastern coast of United States covered with wind farms, and then like along the entire eastern seaboard offshore wind farms. Even then, what they have found is some modification in the precipitation, like, event, some displacement, something like that. We have to realize that, like, that in terms of the amount of energy that is in monsoon, it can easily be done by looking at the potential temperature difference, like between the Arabian Sea and the Indian landmass. That's really, really high. It will be very difficult to.
Scale is very different.
Scale is very different. However, there are, like, those kinds of hypothetical scenarios people have done covering one continent with wind farm and those kinds of things. Then obviously things are very different. Then you can see even slowing down of, like, the Rossby wave, these kinds of things, if you go that large. But if you are looking at these kinds of human scale wind farms, you are going to see effects quite large in the vicinity in terms of dynamics. But it is not going to affect meteorology. I'll just give one example that I think someone said that, like, long time back in the 50s, the US, they had thought of like using a nuclear weapon to dissipate a cyclone. And they saw that the amount of nuclear weapon that would be required will destroy the Earth. That much energy is in a tropical cyclone. So it is just not humanly possible. Unless, what
So
we are.
the committee also said the same thing. The energy of the monsoon and very, very.
It's very, very different.
So this cannot do anything. This was the. Yeah. Of course, we don't have so many winds.
Right. But still, it is not. We are number 5 in the world, so we do have a lot of wind energy.
How would they decide the locations of these wind farms?
So that is a wind farm siting. So first it starts with resource assessment, that you look at wind speed, and mostly from reanalysis and other things. So that, as I pointed out, that is a higher estimate. Some people have started incorporating wake effects. That's too low. So if you have to include wake effects and, like what the German and the Max Planck has done, incorporate both wake effects and recovery. And mesoscale model is perfect for that. Lots of people have tried to do this with large eddy models. But in large eddy simulations, you have periodic boundary conditions. The top boundary is fixed. You can add a constant term. It is not interacting with the atmosphere. So it's not possible. So that is why a mesoscale model is perfect for this, to incorporate both of these. But anyway, so once the wind speed you obtain, then people do what they are mostly from reanalysis that they get. For offshore now, they are using scatterometer data. And then people will go and put a tower there, usually 30-meter tall tower. And then they will get, like, perhaps a few months of data, and then use that to derive some sort of scaling factor to get like the log profile and get like a hub height wind speed. So after that estimate is done, then what they do is local. They'll go look for places. Sometimes it's a very good location, but you cannot buy the land. Sometimes you go to a mediocre location, but the land is cheap. So then those kinds of factors. It always starts with the reanalysis data. Then scaling, downscaling using some local data.
I really enjoyed your.
Thank you.
Nice talk, Somnath. I have one question actually. So you said many of these wind farms are located in the vicinity of agricultural farms. So this kind of momentum effect and then the loss of momentum subsequently in the flow, do they affect the pollination and the movement of pollinators? And do that have effect on this agricultural productivity?
So in the US, most of the wind farms are, this is very different. In the Midwest, most of the wind farms are in agricultural lands. These give farmers they get about 20,000-30,000 rupees dollars a year as rent from the wind farm. So to just build the tower and the access road. So that's a large income for them, number one. But however, there are studies, for example, in Iowa, people have seen that it not exactly addressing that issue, but it affects productivity. Carbon fluxes are different. So because of there is this enhanced vertical mixing, so whenever you have a carbon, if you think of it, the profile is like this, right? More underneath, less aloft. Huh? So now if you have mixing, that will lead to a reduction in carbon. So that means it can have some impact on photosynthesis. And that is something that we see, that carbon concentration and fluxes are slightly lower.
We're talking about that CI/CA ratio, the CO2 concentration in the intercellular space and the outside, which actually drives the CO2 flows to the
Right,
stomata.
I'm talking about what is happening outside, right? So because like, you know, the flux, the profile from near the surface to like, you know, above the hub height of the turbine, that's the critical thing. If you have mixing, whether it is bringing in more CO2 or less CO2, depending on the profile, people have seen that it affects carbon flux. Not pollination and other things.
Okay, thank you.
Wind profiles, yes, perhaps, yeah. I mean, I'm not familiar with things.
Okay.
On, it's on. You can use the mic.
Is it on? Oh.
Yeah.
So you also showed that in the wake region there is drop in humidity, right? So does it mean that it also acts as a sink for moisture, and what is the mechanism behind that?
Well, I mean, I will say that, like, you know, if you ignore the variable and you just focus on the vertical profile, I think that is the best way to explain this. So because no phase changing is happening, right? So if you have a vertical profile in the sense the slope is negative, that you have more near the surface, less aloft. Now, if you have mixing,
It's just because of mixing.
that's it. That's our hypothesis only. That because of the turbulent mixing, that is why if you have with temperature, we have seen it work very well. That like, you know, when you have stable profile versus when you have unstable profile, where it's bringing down cold air, we see a cooling. When it's stable profile, when the vertical profile is negative, then we see a warming. That's something that was our hypothesis. That's what the models are showing. And that's what most of the data are showing. If you look at observations, one thing that they are not finding, like, you know, a daytime warming. And that is because perhaps it is like, you know, by the mostly daytime, it's fairly neutral. Not unstable, because the surface layer in the daytime it becomes neutral very quickly. So perhaps that is the reason. But the nocturnal warming is very strong in all the studies.
Daytime the convectivity is so strong.
Is possible in my head, but people have looked at that, and actually the pressure drop has been, I don't remember the magnitude or anything, but I know one paper that actually evaluated the model using pressure data. I can find out.
Okay,
Yeah.
thank you.
Yes. How this your research helps to wind energy companies, that they take such kind of data and use for their.
Actually, wind energy industry is very pragmatic. They have many issues, like science is just one of them. So when the lot of the wind farms were built at that time, there was a lot of subsidy. So people they just set things up. Now things are changing. The wind energy industry is very interested in resources, because what is happening now, that big companies are coming, foreign companies, and they are buying the. So most of the wind farms that was set up in India in the 10, 15 years back, they are very old. They need replacement. So people are coming. They are looking at who is performing better and why, and they are interested in, like, you know, the next 30 years. That kind of. So many of them are using resource estimation using this approach, that both wake and recovery. You add them, but they do very differently. They don't use a WRF model. What they have done is, like, you know, in there are just wake models. Then they add a constant recovery term coming from the model. So the same approach, but they do it in a simplistic way to do the resources. That way it is a.
Sir, actually, just like you're telling the wind energy companies, just like here in Maharashtra, in the Satara region, there is a Suzlon company, which Dr. Krishnan was also mentioning about that. That localites told that it is dragging out the monsoon from Satara region because that time some rainfall was less. But Dr. Pant's committee told that the monsoon space is much higher, the dimensions are quite high, and that is 100 meter. You told that 100, 200, maximum 300 meter, the wind turbines will go. So that Suzlon, they are producing wind energy, but they have some problem, just like a seasonal problem, because in the monsoon season, the wind the strength is quite high. But other many times that wind, this strength is not that good. So throughout the year, that wind strength, if it is not that, so commercially, how much viable it will be there in a particular place. So suppose somebody does some industry for the wind energy generation.
Oh, yeah, this kind of seasonal variability exists everywhere. Like, I mean, if you look at, so will there be no solar panels in Norway? Right? I mean, 6 months there is no sun. So you have to make this estimate that like, and what definitely the monsoon period is the most productive period. And that is why, like, I mean, my monsoon mission project is to do seasonal, sub-seasonal forecasting of monsoon winds. And I have done many projects. Everybody is interested in the monsoon. I think for the wind energy industry, there is plenty of opportunity to make money just on the monsoon. So the monsoon is a very important thing for us. So they do. I mean, one thing I will say that one question that comes to people's mind when terms of footprint, don't look at just the turbine. You have to look at like, because the fluid is dynamic, how high it will go. So we have extensively looked at this, and it can go, the impact, small or whatever, several kilometers, but it's still not strong enough to affect like, large scale flow. But in terms of monsoon, again, there is plenty of like so much energy that this can drive their kind of annual, generate large part of their annual revenue just from the monsoon.
Priyanka. Hey, it's on. It's on. Yeah.
Hello. Yeah. So you just talked about the mixing in the wake region, like the moisture or the temperature. So what is the altitude we are talking? Is it the height of the windmill, or it extends beyond that also?
Right. So first I will say we don't call these windmills anymore, because the windmills are something to grind rice and atta. These are called turbines because they generate power. Number one, this is a very common nomenclature. People use this. But the important thing is that, so very maximum effect is at the hub height. Hub means that is the tower, and then you have the turbine, right? So you can see the hub. That's where the like towers come from. So maximum impact is there. But the wake that comes out, that spreads vertically also, horizontally, vertically. And the wake can be like, very, but it depends on like how high the wake can go. So the maximum effect is at like, let's say if you have a typical modern turbine, which is 120 meters. So the maximum effect you are going to see at that height. However, because the wake is expanding like a cone, but you think of, this is where you can just use perhaps some sort of dispersion type Gaussian approach. If it is very stable, the cone will not spread too much. If it is very unstable, then the cone will perhaps go like a plume. These kinds of things can happen, but the wake maximum perhaps not more than a kilometer high.
So the mixing goes beyond the PBL, we can say.
I have some papers, yes, but perhaps we would, yeah. So it is in the mesoscale. We have seen signals from models. There are no observations that high. Even the LiDAR, they do not go that high. So from the models, we have seen like, there is an effect beyond the PBL. Maximum effect is in the surface layer, but there are some non-trivial effects beyond the planetary.
Any more questions?
So in terms of mixing, what you can do is do a control experiment and subtract that from a wind farm experiment.
So actually, I work on atmospheric pollution. So I thought of something while listening to your talk. I would discuss with you after this talk.
Definitely,
Yeah.
yes, yeah.
Yeah, Smriti. Yeah.
A very enlightening talk, sir. I'm just curious about with the wake effect, people knowing about it for several years. So there must be some studies that have, kind of found a solution to this problem for the wind turbine fields. Like if first turbine is reducing the momentum for the next one, so can design change or something like increasing the height of the means elevating it or something? These kind of studies must all means have be there. So can you just give insights on that? Like
Yes,
what is the solution for that?
this is an integral part of wind farm layout design. There are many softwares, like some of them are also freely available from the DTU side. They produce WASP software, which is freely available. You can put there are actually competitions. Best design, wind farm design, and large companies sponsor this. You can use AI techniques and other kinds of things. Where can I put to see that minimize the wake effect? So you can stagger them. Like, we have one row like this, the next row is in between. Obviously, you cannot eliminate wakes, but you can try to minimize them. One interesting thing study, but because the wakes expand laterally also, so you can, it's difficult to be completely wake free. You can always be wake free if you put something 10 kilometers away, but you cannot do that because transmission costs are very high. So you have to cluster them in one location, not only for transmission, but grid stability. So within that constraint, try to do this layout optimization. So actually one of my students has a very nice paper on layout optimization using genetic algorithm. Where shall I put it? So you try many different things and it gives you some solution. Another interesting thing that has recently come out that if you can, let's say you have a wind is coming and the wake is in that direction, if you in real time, if you slightly turn the wake turbine, to slightly change the direction of the wake. So real time optimization of wind turbine like veering. So that also improves your performance by, but not too much, 1-2%, which is a large number actually in terms of dollar value. So this is something people are doing all. Common problem, especially in the direction. Yeah. No, I have no idea. I mean, I know that of this problem. This is a very common problem in
There is no
Europe.
answer of all.
No, I mean, it is a structure, it is there. So you have to write an algorithm that excludes it. Yeah.
Yes.
Perhaps a mask or something like that. There is really no other way, because they will show up. They are very big.
Actually, last year I was in NIT Rourkela and they are. So what they did actually, they tried to explore the potential of wind farms to cities. But what I found, I did not have any confidence in their approach. I wanted to ask you that the AWS data from IM located at not very high level, it is being high data good enough to study the
Well, I mean, people use like a lot of, I say, I think if you can extrapolate it and evaluate it, WS is like 10 meter, right? I think. Then also you get it's in the middle of a city, how representative of it, what is the, first you have the displacement height, then you have the roughness length. So then the log profile starts from that. So I think this can be perhaps done if you have perhaps some data from a LiDAR or something like that, and then add some correction factors. If you really want to do it, then it needs to be corrected. That should be
Maybe
the
that is one of the reasons, because you said this potential of these farms are also exaggerated, right? So that
many often are facing that problem.
Yeah, thank you. I think it was really very interesting talk and discussions, and if more, then we can discuss during the tea. But let us give a round of applause to Professor Vaidya. Now I request director to kindly honor Professor Vaidya with a memento. Yeah.
Really enjoyed.
Thank you.
Low level jet.
Yes, yeah.
Much above your.
If you put, it would have done like large. Thank you.
Yeah, thank you.
Let's have a tea. Yeah. Please join for tea. Yeah, you can.